In the last video, we saw how many words there are in real-world corpora and how words are distributed. Most word types are rare. Fortunately, many word types have structure, which is often as simple as the concatenation of multiple units that each contribute some syntactic or semantic information, though for some languages the process can be much more complex. This video is about that structure, which is called morphology. First, let's define a couple terms. A morpheme is the smallest meaning-bearing unit in a language. There are two broad categories of morphemes: stems, which are core meaning-bearing units, and affixes, which are pieces that attach to stems to add some bit of grammatical function or meaning. For example, the word type colder consists of the stem cold and the affix er. With those definitions, we can now define morphology. It's the study of how words are built from morphemes. Languages differ widely in terms of the complexity of their morphology. In the last video, we compared type token ratios for different corpora. How about comparing across languages? Here are type token ratios of languages in Europarl, a corpus containing the European Parliament proceedings. Using this corpus lets us control for the domain and quantity of text as we compare. It turns out that this simple statistic correlates with morphological complexity. English has relatively simple morphology, while languages like Czech and German have more complexity, and for languages like Finnish, it's critical to be able to handle morphology to do effective NLP. Let's look at the families that these languages belong to, shown here in different colors. Similar languages tend to have similar complexity in their morphology. For Romance languages like French and Spanish, it's relatively simple, while the Uralic languages are at the other end of the spectrum. Germanic languages show a broader range. While English is a Germanic language, it's unique in many ways, and tends to have much simpler morphology than its siblings, while German, on the higher end, is notorious for its use of compounding. Linguists categorize types of word formation into a few different categories. Inflection means modifying a word with an affix to change its grammatical function. This does not significantly affect word meaning. Derivation involves adding an affix to a stem to create a new word. The difference between inflection and derivation can be subtle. Derivation is more likely to significantly change the meaning of the stem and change its part of speech, like from an adjective to an adverb or an adjective to a noun, as in these examples, while inflection does not change the fundamental category of the word. Finally, compounding simply combines two words, as in these examples. Usually, the structure of a morphological decomposition of a word is just concatenation of morphemes, but it can be a hierarchical structure as well. For example, the word unbreakable means not breakable, rather than able to be unbroken. Is there ever ambiguity in the hierarchical morphological decomposition of a word? It's rare, but it does happen. For example, with the word unlockable. This can either mean able to be unlocked or not able to be locked, depending on the morphological decomposition. For handling morphology in NLP systems, there are two main types of problems we consider: lemmatization and stemming. First, some terminology. A lemma is the canonical or dictionary form of a word, the form you would look up if you wanted to look up the word in a dictionary. Words with the same lemma typically have the same stem, part of speech, and meaning, roughly speaking. The word form, by contrast, is the full inflected or derived form of the word as it would appear in a text corpus. Then, lemmatization is the task of converting a word form to its lemma. For example, am, is, and are converted to be. And here are some other examples. The task is mostly about looking up the inflected form in a dictionary and returning its lemma. But there are cases where a single inflected form could be mapped to multiple lemmas, so the task can benefit from context information. Stemming is a coarser and simpler procedure which just seeks to remove affixes. It usually uses language-specific, handwritten rules, and is very popular for information retrieval. Here's an example. Punctuation is removed, and words that have been modified are shown in bold. Stems may be words, like with form and transport, but they may not be, unlike lemmatization, which always outputs lemmas. The most well-known stemmer for English is the Porter stemmer, which uses a large set of rules applied in a specific order with the goal of accounting for the most common English affixes while avoiding overstemming. For example, step 1b removes the suffix ing, but only when there is a vowel occurring before the ing. So it's removed for walking, but not for a word like sing. The Porter stemmer works reasonably well for a lot of things, but it does have some idiosyncrasies. It maps some word forms to the same stem that are really quite different concepts, as shown in the examples here. Both lemmatization and stemming seek to neutralize variability due to morphology. But they differ in a few ways. Lemmatization is more likely to be treated as an NLP task and solved with resources and potentially with labeled data and machine learning in order to take context into account. Stemming usually uses manually defined rules, which makes it simpler and faster to run, but there are more potential errors and limitations. We can benefit from these while mitigating information loss by combining them with the original text in sort of parallel streams. Finally, what's caught on recently is to use a data-driven segmenter that splits words into pieces, called subword units or word pieces, based on the frequency of character sequences in the data. The most popular methods are byte pair encoding, which we'll talk about briefly, and the unigram language model from the Sentence Piece Toolkit. These achieve the goal of splitting words into smaller pieces and work pretty well in practice, but the splits don't necessarily correspond to morphological units. We'll see some examples. They've become a standard choice when building large-scale neural net language models like BERT and GPT, so we'll see a lot more of them later in the course. Byte pair encoding was originally developed as a data compression technique that iteratively combines frequent byte pairs in a file into a single byte. Zenrik et al. Adapted BPE for segmenting words, which is the algorithm we'll look at. Here is a sketch of the algorithm. The key operation is a merge, which combines two consecutive units into a single one. At first, units are characters, and after submerges, the units become character sequences. The algorithm performs a sequence of merges based on the current unit sequence counts, choosing merges greedily. You can decide the stopping point based on how aggressively you want to be splitting words. The more merges you do, the larger your resulting vocabulary and the less splitting. Rather than go through the algorithm in any more detail, let's look at some examples. Here's an unknown word from the test set of a movie review dataset. Two @ symbols followed by a space are used to indicate a split, which differentiates a space within a word from a space between words, so there's no information loss, and the original text can always be recovered. Here's another example. Common words are almost never split, even if they consist of multiple morphemes, like the word minutes. Rare words tend to be split, and sometimes this corresponds to a valid morphological decomposition, as in the case of preferred, while other times the split looks noisy, like with spending. The big advantage of this method is that we can reduce our vocabulary size and handle unknown words. This can make modeling and learning easier, as we'll see later in the course.